So we can continue with the last real talk of the session. And it's a pleasure to have Francesco Galvagno here. He's going to tell us about Branes now and integrated correlators. Take it away.
Thank you, Daniela. I thank also the organizer for this chance to speak here. Yeah, I mean, today I'm going to talk about, again, N=4 integrated correlators, but dual to different processes, which are some special scattering amplitudes in presence of branes as well. And this is associated to this series of papers together with some people at Queen Mary University and also Torino University. So let's start by giving some general motivations. We are studying scattering processes in the context of ADS-CFT, and in particular here we basically present some QFT technique, some special QFT techniques in N=4 super-EM mills that have a certain string theory interpretation, and in particular, thanks to this ADS-CFT dictionary, boundaries, endpoint, general correlation function are associated to some special superstring scattering amplitudes, and in particular, in general, if one considers local operators on the boundary side, this corresponds to closed string amplitudes. The technique that we are actually that we are considering now are these integrated correlators in N=4 super-EM mills that have been developed in a long series of papers in the last 5 years, and this has been exactly discussed by many other papers, but by many other talks today and also in the upcoming days. And the main technique involved here in this game is supersymmetric localization, and the concept behind this very special technique in superconformal field theories is that it allows to consider a path integral of a general quantum field theory and to reduce it, thanks to the presence of supersymmetry, to a finite dimensional integral, in this case, a special matrix model. As we said before, we have always seen some integrated correlators that are dual to closed string scattering amplitudes. In this case, we are going to consider some scattering processes in presence of extended branes. And in particular, these are the two processes that we are going to discuss today. The first setup is a 4-point correlators in presence of special determinant operators. And in this case, the presence of these heavy operators create a certain class of D3 branes in the bulk. On the other hand, in the second part of the talk, we're going to consider a 2-point function of integrated correlators in presence of a line defect, which in this case breaks conformal symmetry already on the boundary. So this is the configuration, and here this special setup is dual to some graviton scattering of a long string in the bulk. So let's start with the first process. Let me give some more details about this 4-point function. It's a 4-point function in presence of two light operators, which are these O2 operators corresponding to scalar operators with conformal dimension 2, which lie in the stress tensor multiplet of N=4, and they can be written in terms of traces of some scalar combination of scalars of N=4 super-EM mills. But the interesting part is associated to these operators D, which is defined as a determinant over the gauge group, which we consider to be SUN. This special D of X operators are still half BPS, and this means that their conformal dimension is fixed thanks to supersymmetry, and in particular is fixed to be equal to n. So these operators become very heavy when we consider the large n limit. Indeed, I mean, they can be considered also from the field theory side like baryons. I mean, the baryon equivalent operator in N=4 super-EM mills, and from this perspective, it would be already a very interesting operator. But also, in the ADS-CFT correspondence setup, this is dual, a configuration where you insert a couple, a pair of these determinant operators is dual to a presence of a giant graviton D3 branes extended along S5 direction. So, in particular, we see that this 4-point function of local operators in the large N limit becomes a string scattering process in presence of a D3 brane. And in particular, we consider, like we were seeing this morning, a 4-point function of this kind, which is fixed by superconformal symmetry. The important part here is basically this function HD, which is called also reduced correlator, which is a function of the two conformal cross ratios, U and V, and the complexified coupling tau. And then we apply this localization procedure for integrated correlators. Here, I don't have time to go through the whole process, but the idea is that we start from a flat space path integral. We apply a conformal map to uplift it to a four sphere, and then we start deforming the n=4 partition function by some special deformations. This morning, we have seen in particular the mass deformations, but in general, it can be any possible deformation preserving at least n=2 supersymmetry. Each of these deformations will be associated to some integrated insertion of some local operators, as we see here. And since we are preserving at least n=2 supersymmetry, we can then apply supersymmetric localization, thanks to Peston's prescription. And we lie down then to this matrix model, which is a matrix model of this n=2 star theory. At this point, if one starts taking derivatives with respect to this lambda A, one gets basically correlators integrated with a special integration measure. So in particular, applying the full superconformal symmetry, one ends up with this integrated correlator in presence of this measure mu of the two conformal cross ratios of this function HD. And this is equal, on the other side, to a matrix model quantities, which would be basically a bunch of derivatives of this special deformation. This whole configuration will be then given in terms of a unique function, which is a function at this point only of the complexified coupling tau and of the number of colors n. In our paper then, till now, this whole procedure is pretty general for any 4-point function. In our case, we had to basically develop some special matrix model techniques to deal with these heavy operators, which are these special determinant operators. I don't have time here to go into the details for these special techniques. I will directly jump on the results, which are this one.
Can I ask?
Of course, yes.
I should have asked.
Yes.
So when you say, I'm saying you're saying these determinant operators because they scale with n and so on.
Yeah.
But you say that they are D3 branes on the string theory side. Do we know that?
That's a good point. Actually, this is, there are people that studied this kind of, these special correlation functions in presence of these determinant operators in the past, and they have seen that actually correspond then to some holographic computations on the dual side. Here, for this special 4-point function, nobody ever understood this or claimed that. The point is that once that we then apply this full localization procedure and so on and so forth, and look at this final result, we see that in particular, for example, from this function, we see that this result in the top limit, so in the large n and fixed lambda, this is organized in terms of power of this 1/n, which kind of mimics the fact that you are computing something somehow in presence of some open strings and not just closed strings, because if not, this series would be organized in terms of n squared, right? 1/n squared. So we're not saying that we are completely sure, but we have a lot of indications now. Both in this Toft limit and also in this large n finite tau limit from similar perspectives. But yeah, thanks for the question.
I would say perhaps the modular one is the most.
I agree.
The one that is, I wouldn't say a smoking gun, but like you can do a string theory calculation with
Absolutely.
a Brane, and you're going to get the same
Absolutely.
result.
Absolutely. This is exactly a clear sign that somehow you are computing something in presence of a D3 brane. Because, yeah, like Daniele was exactly pointing out, if one considers, top limit, one gets this expansion, and then, as we were seeing before, you get some exact results in lambda. But then, if one goes to the large n finite tau limit, here you can re-express these full results in terms of some SL2Z invariant functions. And in particular, here, this E1 function appears that, this class of functions was not appearing in standard 4-point function of trace operators somehow, where you only had E3 half, E5 half, 7 half, and so on and so forth. This E1, which also contains this log lambda term that Hinek was actually mentioning before, this is clearly assigned, this is consistent with some previous Brane bulk amplitude computation done by Michael Green and other collaborations in the past. So somehow, thanks. This is why we are kind of, not completely sure, but kind of optimistic that we are actually computing a scattering amplitudes in presence of a D3 Brane. Okay, let me now move to the second integrated correlator that we are going to discuss today, which is the 2-point function integrated correlator in presence of this line defect. Also here, I'm going to be fast, but in this case, already the superconformal setup is less clear and also less studied. But again, if one puts this extended line operator in a conformal theory, the final function, this final 2-point function will be expressed in terms of two conformal cross ratios, which are these two distances here, psi and eta. We consider then the simplest case, which is the half BPS Wilson line, which can be written in terms of this phase factor of the gauge field coupled with the scalar fields of n equal 4 super Yang-Mills. And the 2-point function here, and this is kind of different compared to the 4-point function case, can be written in terms of three different R-symmetry channels. Here I'm just writing the first one because the other two are at the moment not approachable using these standard localization techniques. So we just consider this F0, but then we can apply basically the previous machinery for this integrated correlator story, again, also in presence of this line defect. So we start from the flat space, we insert also this Wilson line, we go to this fourth sphere, you apply, deformations, localization, you end up with a matrix model quantity. And again, taking derivatives means somehow considering some integrated insertions on the flat space. And this allows to basically define, as also Daniele was teaching us this morning, this integrated correlator in presence of a defect, which is again a function of tau and tau bar, and the number of color n. The result in this case is highly non-trivial. First of all, we were able to derive an exact function for this integration measure, which is, very complicated in all these intermediate steps here. But in the end, the final result is extremely simple. This integration measure in terms of the two conformal cross ratios is basically 1, it's just a constant. And instead, from the matrix model side, we were able to also, in this case, computing in the large n fixed lambda limit the leading order, which is this function here, again, in terms of a convolution of Bessel functions. In this case, as we were seeing this morning, this defect correlator is not modular invariant, and in particular, for example, the S transformation of SL2Z now transforms the Wilson loop integrated correlators into the Toft loop. And so in this case, there are many interesting modular properties that are yet, to be fully understood somehow, and as we have seen in Daniele's talk. So let me jump to the conclusion, which are very, very brief, because this topic is somehow very at its start, somehow. Today, we studied two different classes of integrated correlators, which are both associated to some dual scattering processes in presence of D branes. In one case, a 4-point function in presence of these determinant operators. On the other case, a 2-point function in presence of a line defect. In the future, of course, it would be very interesting to study different classes of heavy operators in the 4-point function to explore from this side also maybe different kind of configurations. From the line defect perspective, it would be very nice to study different deformation parameters to achieve also different R-symmetry channels, but also try to go beyond, the line defect configuration and study maybe higher dimensional defects. The process could be kind of similar depending on how much supersymmetry one is able to preserve. And then, of course, it would be nice to fully explore the SL2Z properties of both of these two setups. And with this, I can stop here and thank you all for the attention.
Questions, comments? Yes, please.
Yeah, you quoted results of Brane and Bachas and others on string scattering of D-branes,
Yes.
Against which you cross-checked. Are you already at the point where you can predict higher order results for such amplitudes, say higher order alpha prime, higher genus?
That's a good point. This whole localization computation is definitely not easy. And so already getting these two first results, which are basically the disk amplitudes and the annulus amplitudes, basically, were already kind of hard. We understood which would be the possible direction to go beyond to higher orders. This would be extremely needed to go beyond also in this expansion here. But at this point, I think we are not that close there to expand this expansion that much, let's say. But it would be, of course, definitely interesting. Yeah.
Not sure which one are still BTS protected, right? Because just
Also.
like in the 4-point function of all tools, after a certain point, as you know very well, you're not BTS protected
Yes,
anymore. So there is no string theory waiting.
Yes.
Localization gives you something, but you don't know what you have to compare against these things.
Somehow localization gives you a certain coefficient, and you should be able then to recognize this coefficient is associated to R to the 4, D4, R4, and so on and so forth. This was the story for the 4-point function. And here it would be something extremely similar for the D3 Brane low energy expansion. And at certain point also there, supersymmetry is not powerful enough to fix exactly the function that you have, and consequently also localization is not powerful enough to fix then a unique coefficient in this case.
Just a few privileged alpha prime ones,
Yes.
but not generic ones.
Yes.
Yes, please. Yeah.
Maybe a technical question.
Yeah.
In the relation to the to supersymmetric localization, I think on the previous slide,
Yeah.
what is this differential operator delta D, which you didn't?
Yeah, that's a good point. That's a good point. It's extremely complicated in principle. This is all hidden here in this sentence. Somehow, this definition of this determinant can be then also re-expanded in terms of trace operators. And here you would get basically trace of phi to the n plus all the other multi-trace operators. And you would have infinite number of them, of course.
So it's a linear combination of these.
Yes. The point is that, yes, exactly. The point is that it's very hard to compute this in this way using standard localization technique and the usual orthogonalization procedure and so on and so forth. We kind of reverse the engineer, but this is a very technical point. I think we can explain you then more privately, or whoever wants, I can explain more in details also at this point. Yes.
Can I ask a question?
Of
Can you
course.
go to the fixed Landau expression? Yeah.
This one.
Can you, or maybe yes, please. No, the one where you had the chi kernel as well.
The chi, this one, this chi term.
No, sorry, this is for D, for the line defect, sorry.
Yes.
Yeah, very good, here, yeah. Have you computed the non-perturbative effects at large lambda for this object? Do you expect to get something different from, say, the one that you get in 402s, or?
That's a good point. Here, we stopped here, but actually, I think we could even go beyond this order.
No, but even just
Yes.
this order, more or less at any order, any genus order,
Yes.
they all look the same, more or less.
Yes,
It's just
I
come from
agree.
the fact that you have two vessel J, right?
Yes, I agree. Here, it's really a combination of J and I. This I comes exactly from, the Wilson line. Yeah, that's a good point. I think it would be super interesting to study. I don't have a direct answer now, but
Because
yes.
unlike Paolo's talking here, you're going to get an asymptotic power series
Yes.
in lambda at large lambda. So you
Absolutely.
could just use directly the
Yes. Yeah. That's. I mean, I think the story would be, kind of the same. I don't know which kind of function you would have to compute this discontinuity term of, but yeah, somehow the idea would be very similar.
Very good. Yes, sorry, please.
There was this Eisenstein series at the delicate value s equal 1.
Yeah.
Does it exponentiate?
This.
Could it be that the O n to the minus 3 half terms are such that you can absorb it into an exponential?
That's a good point. I don't know. It can be. I'm not fully sure. I mean, it would be nice, of course, but I don't know which would be then the dual interpretation at this point. But maybe I don't know. I wouldn't be so optimistic that this could be possible somehow. But
There's a holomorphic counterpart to that gadget, which in other situations is famous for exponentiating. So
okay.
it's just one way.
Okay.
This happens to be the case here.
Good. I don't see any more questions, so let's
Thank you.
Let's go.